All right, hello, my name is Joshua Stucky. I am a graduate student at Kansas State University, and today I want to talk to you about a research project that I recently completed concerning the distribution of Gaussian primes in narrow sectors. Now, I only have 20-25 minutes for this talk, so instead of going through all of the methodology that I used to prove my result, instead what I want to do is talk a little bit about the motivation behind my result, why it's something natural that you might want to look at, why it's interesting, and then talk about just the statement of my result, what it means. If we have time, maybe I can indicate some some of the methodology used, but I think I'll just content myself with talking about the motivation and the statement of the result itself. As a disclaimer, I will say that I'm going to assume a basic knowledge of multiplicative number theory for this talk. So if you're listening, I am going to assume that you know like what the von Mengelt function is, what the Mobius function is, what the Riemann zeta function is. I don't really have time to go through all the definitions of those things, so I'm just going to assume that little bit so that it'll make the talk a little bit more expedited. Okay, so where does our problem begin? So there's the classical problem of counting primes in short intervals, and Huxley's result is one of the sort of classical results in this area. Back in 1972, he proved that if you have an interval of starting at x and then going up to x as small, or going up to y as small as x to the 7/12 plus epsilon, then the sum of the von Mengelt function over that interval is going to be asymptotic to the length of that interval. And one of the main corollaries is that every short interval of this kind, this is what we call a short interval because this theta is less than 1, every short interval of this kind is going to contain a rational prime. Reason for that is because this sum, the dominant term, the main term of this, is a sum over primes. And if this isn't here, then you have only this error term, but this would violate this asymptotic up here because y is greater than x to the 7/12, and 7/12 is bigger than a half. Conditional on the Riemann hypothesis, you could take y as small as x to the 1/12 or 1/2 plus epsilon. Maybe x to the 1/2 times a few powers of log. But anyways, so Huxley's result is proved using zero density estimates for the Riemann zeta function. So what is a zero density estimate? So if I let n of sigma t be the counting function for the non-trivial zeros of the Riemann zeta function, it's going to count a number of zeros where the real part is greater than sigma and the imaginary part is bounded in absolute value by t. So we're counting them in sort of these rectangular areas. Then Huxley's zero density estimate, which immediately implies what he had before, is that n of sigma times t is bounded by t to the 12/5 times 1 minus sigma times some power of log t. You don't really care about how many powers are here, at least in the context of this problem. There are some places where you would want to know how many logs you have. You want to try and get as few as possible. There are these things called log-free zero density estimates, but in our case, we don't really need to worry about it. B is just some positive number that doesn't really matter. And so notice that the 7/12 that we had before is precisely 1 minus 1 over 12/5, and so that's how that exponent is being computed there. That's where it comes from. And conditional on the Riemann hypothesis, or even something weaker like the density conjecture of Montgomery, you could take this 12/5 equal to 2, and that would give you the 1/2 from earlier. But anyway, so this is how Huxley proved his result. Later on, Heath-Brown came and gave a different proof using a combinatorial identity for the von Mengelt function. And his identity states that for any n less than or equal to some fixed value x, and then j greater than or equal to 1, it's just some integer, the von Mengelt function decomposes as a linear combination of these sort of divisor sums where you have a sum over all the ways to write n as a product of 2j things, where you have log of one of them, a bunch of ones, and then the Mobius function evaluated at the latter j of them, where the size of those is actually bounded by x to the 1 over j. Now, you look at this, and you're like, how does that at all simplify my problem? So the point of this is if you sum against an indicator function for an interval, or maybe some multiplicative character thrown in as well, you can divide all of these variables m sub I into dyadic intervals and then essentially what you've done is you've decomposed your sum of n less than or equal to x, or x between, or between x and x plus y, something like this. You've decomposed that into a linear combination of a power of log sums. Throughout this analysis, we're going to be okay with losing powers of log, into a linear combination of sums of this form, where you have a bunch of arithmetic functions, a bunch of smooth functions. You have log, which is nice and smooth. You have a bunch of ones in here, and then you have these unknown functions, the Mobius functions, evaluated at these variables. But your saving grace is that you can control the size of the variable that you're plugging into the Mobius function. And so that's what this 1 over j does up here. You can regulate this parameter and kind of, save something, because you know that the sums over these variables, the j plus 1 to 2j, those are going to be somewhat short in the sense of, being less than x to the 1 over j. Okay, so that's kind of some background on primes in short intervals. So the sort of thing that I want to talk about is the distribution of Gaussian primes. So what are Gaussian primes? So if I look at the Gaussian integers and I look at the prime ideals in the Gaussian integers, well, the Gaussian integers are a principal ideal domain, so I can identify each of the prime ideals with any one of its generators. And in general, you could sort of take your generator to always lie in, say, the first quadrant. It doesn't really matter which generator you take. Some notation here, we're gonna, if you give me an ideal, a plus bi, then I'm gonna denote its norm by its squared absolute value and its argument by whatever its actual argument is, but mod pi over 2. So the pi over 2 is 2 pi divided by the number of units in the ring Zi, which is 4. So that's why we have pi over 2 here. So the argument is well defined on ideals, as is the norm. Doesn't matter which generator I take here. These two quantities are going to be well defined on ideals, not just complex numbers. And then we have this theorem of Hecke, or I don't know if it was Hecke or some later person using his results, but essentially you have this result which says that if you're looking at sectors in the complex plane and you look at Gaussian integers in those sectors, then if you restrict the norm by x and the argument of a prime ideal in between these two numbers, so you're inside of the sector, then these the distribution of these is like the kind of what you would get from the prime number theorem. So you have this normalizing factor coming from the number of units in the field, and then you have beta minus alpha, so kind of a measurement of how big your sector is, and then the logarithmic integral here, which is going to give you like x over log x as a main term. And then here we have an error term where you can only save powers of log x. You can't do any better than that. So as soon as your sector is smaller than some negative power of x, then your error term just dominates here. And this is not a very, this isn't a particularly meaningful statement. You just have something which is dominated by an error term. And notice here the beta minus alpha, it only matters the difference between these two. It doesn't, the actual values of beta minus alpha is not really relevant. You just care about how big it is. So this actually tells you that primes equidistribute in the in sectors in the complex plane. So what you can do is you can think about, okay, well, what if I take my sector to be very small? Let's say it's some power, some negative power of x. Well, now we're sort of getting into the same kind of problem that we had with primes in short intervals. So here, if we're thinking about what these sectors look like, this is kind of the picture. These are the blue dots are all Gaussian primes, and then the sectors that we're sort of thinking about are these sort of triangular shapes with circular edges at the edge. So let's talk about Gaussian primes in narrow sectors now, kind of what I said before. So there's this classic folklore problem. I don't know exactly who said it first or who wrote it down first, but there's this conjecture that there are infinitely many rational primes that are of the form, they're one more than a square. So p equals n squared plus 1. Proving that this is true, well out of the reach of current methods. Good luck if you wanted to try and sit down and prove this. More power to you. It's going to be really hard. There are a number of kind of results in this direction, mine being one of them. But as an approximation to this conjecture, what we can do instead is say, okay, well, I'm going to look for infinitely many primes where there's a sum of two squares and the second parameter b is small. And so your goal would be to get theta equal to negative epsilon for some positive epsilon, some parameter. It doesn't matter how big it is, but you just need it to be less than 0. You couldn't take it equal to 0 because you can only get epsilon right here, so you need it to actually be negative, and then that would give you this conjecture here. So your goal is to try and take theta as small as possible in this sort of new setup. And the reason that we talk about narrow sectors is that, you know, if I have a prime that's a sum of two squares, it's really the norm of a prime ideal in the Gaussian integers. And so really when I ask for b small, I'm really asking for something like the second coordinate, the imaginary part of my Gaussian integer, to lie close to the real axis. So I'm really looking for prime ideals in narrow sectors. So few results, old and new. So if I let lambda of this math frac A denote the generalization of the von Mangold function to the Gaussian integer, so I'm going to take the norm of the ideal if my ideal is a power of a prime ideal and 0 otherwise, then I can state a few theorems. So the first that I want to talk about is due to Ritchie. So this was in his thesis in 1976. So given any phi in 0 to 2 pi and x sufficiently large, and delta greater than x to the negative 3/10, then if you sum all of the ideals in this sector that's emanating from the origin with internal angle of size delta, then you get what you expect for your asymptotic. You get x times delta, which is really just a measurement of the area of your sector, and then you have this normalization factor 2 over pi out front. And so notice the norm here has to go all the way down to the origin. We're taking the norm just less than or equal to x. We're not taking the norm in a particular interval. This delta here, greater than x to the negative 3/10, conjecturally you could take this, you know, x much, I guess, large, or the exponent here you could take closer to something like 1/2 and negative 1/2 and still get an asymptotic. Similarly, it would kind of follow from the generalized Riemann hypothesis for Hecke L-Functions. But anyway, so this is the theorem of Ritchie. Let's just keep in mind this negative 3/10 here. So the corollary to this is that there are infinitely many rational primes that are a sum of two squares where the second number is less than p to the 1/5 plus epsilon. Let's go on to this result of Coleman. So this was a little bit later in 1989. So now instead of looking at ideals that are you know near the origin, I'm gonna not restrict the norm of my ideal to go all the way down to the origin. I'm gonna now allow it to also lie in some interval. If I look at the sum of the von Mangold function in this more generalized sector, then here I'm going to get the expected sort of asymptotic that I want, so long as both of my parameters are sufficiently large. So as long as both of these are large is really a statement about the perimeter of this sector. So long as the perimeter is sufficiently large in the sense of both of their parameters here being of these sizes, then you get the expected count of prime ideals in these sectors. Coleman didn't exactly prove this, but it follows quite readily from the result that's proved in the paper that I'm referencing in this 1989 reference. His is actually a zero density result, and I'll look at that later. Okay, so what is my result, the thing that I actually proved? So very similar. If I take you know if I take these parameters in this way, so the same sort of sum, but now my parameters, I'm gonna not care about the you know how big each of them are individually. I now care about the product of these parameters. So long as that is sufficiently large, then you get the expected number of prime ideals. So Coleman's result kind of says so long as your perimeter is sufficiently large in the sense of these two parameters being large enough, you get the expected number of prime ideals. My result says so long as your area is large enough that you get the expected number of prime ideals. Sufficiently large in the sense of it being greater than x to the 7/10 plus epsilon. And conjecturally, you could take this greater than x to the 1/2 plus epsilon. But anyway, so this is the result that I proved. Notice that the 7/10 is 7/10 minus 1 is -3/10. And so if you took delta equal to x to the -3/10 plus epsilon, and you took theta equal to 1, then you would still have this inequality holding, and you would recover Ritchie's result. So my result is really a generalization of Ritchie's result. Unfortunately, it's not able to improve that 1/5 exponent, but it is able to answer the question of looking at prime ideals in these slightly more general sectorial regions. Sectorial? I don't know if that's a word. Sectors. But anyways, so the kind of regions that I'm talking about, so the ones that Ritchie's theorem deals with are this very long and narrow one emanating from the origin, but mine and Coleman's theorem allow you to look at these slightly more general sort of geometric regions like so. Okay, and it even allows you to look at these sort of very narrow bands and shapes like all these. But anyways, these are the prime ideals in the Gaussian integers up to, I think, with their norm bounded by 10,000 is how I computed this picture. And then, of course, only in the first quadrant. So anyway, so kind of what exactly goes into the proof of my theorem, what's really happening. So if I recall the notation I had before, the norm of an ideal and its argument, then I can define angular Hecke characters, or really just Hecke characters with conductor, the ideal generated by 1. I can define them by this, so the number of units in the field times I times m, which m is this parameter here, times the argument of the ideal. So this defines a multiplicative character on the ideals of the Gaussian integers, and then with those characters, I can attach an L function called a Hecke L-function, where for real part of s greater than 1, I define it in the analogous way that I define the Riemann zeta function. So I have the character up here acting on the ideal of the field, and then instead of just in the bottom, I have the norm of the ideal raised to the power s. And just in the same way that you can write the Riemann zeta function as a product over primes, you can do the same thing with a Hecke L function. You can write it as a product over prime ideals. I should say the ideal 0 is excluded here. These are over non-zero ideals. But anyway, so just like the Riemann zeta function, it's going to have an analytic continuation to all of the complex plane. If m is not 0, then you actually have an entire function. It's going to be defined everywhere, even at s equals 1. And if you are at m equals 0, then your L function is going to factor as the Dedekind zeta function for the Gaussian integers, which is just zeta of s times ls chi. Chi here is the non-trivial character mod 4, the non-trivial Dirichlet character mod 4. Just like the Riemann zeta function, these satisfy a self-dual functional equation. So if I take the L function, then I complete it with its gamma factor, then I obtain, or you can show that this quantity satisfies a functional equation just like the Riemann zeta function does. And just like the Riemann zeta function, you can define a zero density estimate for it. Now it's a little bit different. Instead of just looking at one of these L functions and looking at the zeros of it, I'm actually going to look at zeros of all of the L functions for the parameters where the absolute value of m is bounded by some parameter capital M. So this is really counting the number of zeros of any of the L functions with m bounded by capital M, the real part bounded by sigma, bounded below by sigma, and then the imaginary part bounded by capital T. So if I define this zero density estimate, then I can kind of indicate what the essential difference between my result and Coleman's result is, why they look different, why you sort of get different things out of them. So here, if I write my delta, the internal angle of my sector, if I write that as x to the negative alpha, and I write theta, the interval for my norm, if I write that as 1 minus beta, or the exponent for x on the interval of my norm, then Coleman's theorem needs the sum of those two parameters to be less than 3/10, or I'm sorry, my theorem needs the sum of those parameters to be less than 3/10, and Coleman's theorem needs their maximum to be bounded by 5/24. And so the whole range of parameters is like something like this. So this is the like alpha down here, beta up here. It doesn't really matter which order. But so long as it lies in this blue region, then you can obtain an asymptotic estimate for the number of prime ideals with in these sort of regions with these given parameters. The essential difference is really coming from the kind of zero density estimates you can prove. So with this Riemann zeta function, you really only have like one kind of zero density estimate you can prove. But for this family of Hecke L-functions, you can actually prove two different kinds. So you can prove one where you have a product of the parameters and bounded to some power. And then you can have one where you have the sum of the parameters bounded by or to some power. Notice if I take the 2 here, this is really just the same size as m plus t squared up to some constant. So really there's a 24/5 right here. Instead of the m squared plus t squared, you can think of this as m plus t to the power of 24/5, and that's what's giving you this 5/24 here. And then likewise, the 10/3 is giving you the 3/10. I should say this first zero density estimate is technically conjectural. The results of my paper use a Heath-Brown's identity, which is a generalized version of the one that Heath-Brown proved, but it doesn't actually prove this zero density estimate. I'm fairly confident that the inputs used in my paper could be used to prove a zero density estimate. When you go through and you look at Heath-Brown's method versus Huxley's method, all the inputs are really the same, but you just use them in kind of different ways. So these inputs include things like a large sieve type estimate for characters, a hybrid large sieve estimate, a moment estimate for the Hecke L-functions, a zero free region for the L-functions, maybe even something like a short interval estimate for the moment of a L-function. Yeah, things like this. Maybe even a subconvexity bound. I'm just sort of naming things that go into this. But you use both of those for using Huxley's method and Heath-Brown's method. So I'm confident that the methods used in my paper could be used to prove that this zero density estimate, but it is technically conjectural at this point. But if you were to read my paper, you would see a quantity that looks essentially like this. It's not the number of zeros, but it's a quantity which is quite analogous to it. But anyway, so yeah, that is the essence of my theorem. Ritchie, just as a side note, his theorem, he didn't have the exponent on t, so it was just t to the power of 1 times m to this power right here. Okay, and that's about all the time that I have. I have one more slide I could go through, but I don't want to spend too much time on other stuff, so I'll just finish there. Thanks for listening, and I hope you learned a little bit about kind of what my research looks like, what kind of problems I'm interested in, and yeah, so thanks a bunch.